So what is a compound angle? It sounds a lot more complicated than it actually is. A compound angle is basically just an angle made up of the sum of two or more angles. So for example, sine of theta 1 plus theta 2. And it can be the sum of two or more angles. So it could even be, for example, cos of A plus B plus C. Or even something more funky, such as tan of x plus theta minus alpha plus capital Q. And note that a compound angle can include the sum or the difference of two or more angles. So once you have a compound angle such as this, the question is, can you further simplify this or represent it in a different way? And I think just on looking at it, the first instinct would be to say that, for example, cos A plus B plus C is equal to cos A plus cos B plus cos C, which would be applying the distributive law to it. But unfortunately, nope, the distributive law doesn't apply to compound angles. And what's the distributive law? The distributive law says that multiplying by a group of numbers added together is the same as doing each multiplication separately and then adding them. So for example, when multiplying 2 times the bracketed terms of A plus B, by applying the distributive law, you can get it as being equal to 2A plus 2B. But this doesn't work for trig functions, such as sine, cos, and tan. And that's because, unlike the number 2 over here, sine, cos, and tan aren't really variables. They're more just a sort of notation to indicate specific ratios. Meaning that sine A plus B is not equal to sine A plus sine B. And on a similar note, sine A minus B is not equal to sine A minus sine B, cos A plus B is not equal to cos A plus cos B, and cos A minus B is also not equal to cos A minus cos B. And these would apply to tan as well. However, different ways to simplify these various functions have been determined, and these are known as the compound angle identities. And those are as shown in this border over here. So I use alpha and beta to represent two different angles, and the reason I use these funny symbols is because this is how they're described in the formula sheet you get in your exam paper. So it's worth getting used to this form from the very start. So sine alpha plus beta can be simplified to sine alpha times cos beta plus sine beta times cos alpha. While you don't need to know these by head, it's pretty simple to understand the basic idea, where it's just sine of one angle times cos of the other plus cos of one angle times sine of the other. And for sine alpha minus beta, it's sine alpha cos beta minus sine beta cos alpha. So it's pretty similar to the previous one. However, the order in which the angles appear does have an effect on the simplified term, where you have to have the sine of the first angle times the cos of the second angle being subtracted minus sine of the angle being subtracted times cos of the first angle. So those are the compound angle identities for sine. Then for cos, you have cos alpha plus beta is equal to cos alpha cos beta minus sine alpha sine beta. So it's a slightly different form than the one for sine, where this time you have cos of one angle times cos of the other minus sine of one angle times sine of the other. But unlike for sine, where when you are adding the angles, you are adding the two terms, this time when you're adding the two angles, you're subtracting the two terms. And when you're subtracting the two angles, you're adding the two terms, where if you have cos alpha minus beta, it's cos alpha cos beta plus sine alpha sine beta. So it probably sounds complicated and sort of like mumbo jumbo right now, but once you've applied it a few times, it becomes pretty simple. And as earlier mentioned, in the exam, you won't need to know these forms by head. You'll be given them in the formula sheet. So even if you don't get used to them, you can still just refer to the formula sheet and apply them. Here's an example. The question asks, what is sine 50 plus 30? And by applying the compound angle identity for the addition of two angles with sine, this becomes sine 50 cos 30 plus cos 50 sine 30. Then you can further simplify this by substituting cos 30 and sine 30 with the values from the special angle triangles, where cos 30 is root 3 over 2 and sine 30 is half. And at this point, you wouldn't be able to further simplify it just by hand, so you could just plug these into the calculator, which gives the answer as 0.98. And if you were to get this sort of a question into the exam, you'd probably notice that, okay, I could just do the simple addition of this, which would give 80, and I could just calculate sine 80 to get my answer. But if they were to give it to you in this form, where 80 is split into 50 and 30 and then added, it would imply that they want you to apply the compound angle identity. But the nice thing about this in the end is that you can compare the final answer you get to sine 80 and verify whether it's correct. Let's look at another example. Show that cos 75 equals to root 6 minus root 2 over 4 without using a calculator. The strategy here is to first split cos 75 into some more familiar numbers. The most logical would be to split it into 45 plus 30, since you know the special angle values for a triangle with 45 degree and another one with 30 degrees in it. So once you split cos 75 into 45 and 30, then you can apply the double angle identity for cos, which was this one, where you're adding two angles, which would be cos of the first angle times cos of the second angle minus sine of first angle times sine of second angle. So cos 45 cos 30 minus sine 45 sine 30. Then just substitute these with their values, meaning 1 over root 2 for cos 45, root 3 over 2 for cos 30, 1 over root 2 for sine 45, and 1 over 2 for sine 30. And when you do the multiplication, you'd end up with root 3 over 2 root 2 minus 1 over 2 root 2. And since they have the same denominator, you can combine them nicely into a single fraction to give root 3 minus 1 over 2 root 2. We've got an answer, but it doesn't exactly look like how it's supposed to in the question. So we have to manipulate it a bit. If we try to get a root 6 for this term, a root 2 for this one, and a 4 for the denominator. The easiest number to look at for reference is the number 1 over here. Since we need to transform a 1 to a root 2, we can do that simply by multiplying it by root 2. Therefore, if we multiply this whole fraction by root 2 over root 2, we should be able to get the required fraction from the question, where indeed root 2 times root 3 would be root 6, and root 2 times 1 would be root 2, then 2 root 2 times root 2 would be 2 times root 2 squared, which is just 2 times 2 or 4, finally giving root 6 minus root 2 over 4, as required by the question. And to conclude the question, since it specifically asked us to show something, even though we've arrived at it, it's nice to end it off with just a bit of a flex and just say, hence shown. Just to declare that you have indeed met the requirement of the question. Let's look at another example. Evaluate the following without using a calculator. Cos 35 times sine 65 minus cos 55 times sine 25. So it's a little bit tricky on first appearance, but the trick here is you need to try and get it into the form of one of these identities. And how you could do that is by changing the sine 65 to a cos term using the cofunction identity, and then changing the cos 55 to a sine term, again using the cofunction identity. And what that would lead to is cos 35 times cos 25 minus sine 35 times sine 25, which is similar to the form of the compound angle identity for adding two angles inside the cos brackets. And those two angles would be 35 and 25, since they appear in both terms as required. So this would be simplified to cos of 35 plus 25, which is just cos 60 or 0.5. But that's not the only possibility. You may be wondering, what if I tried changing the cos 35 to sine and the sine 25 to cos instead? That would also work fine, and in that case you'd end up with sine 55 sine 65 minus cos 55 cos 65. And if you take the negative outside the bracket, you would get negative cos 55 cos 65 plus sine 55 sine 65, which is as required for the form of the addition of two angles for cos, which in this case would be the addition of 55 and 65, giving a value of minus cos 120. Then what to do? This 120 can be rewritten in terms of 90 as 90 plus 30. And as we know from earlier, the cofunction term for cos in the second quadrant is cos 90 plus theta equals to minus sine theta, meaning minus sine 30. And the two minuses just cancel out, giving sine 30, which is just 0,5 as we got previously. So doing it this way would definitely take probably like double the time, because almost 2 times as many steps and a little bit of thinking, but it would still give you the correct answer. And even in the exam situation, if you went down this route and got stuck somewhere, you'd probably eventually realize that you could also do it the other way, and it wouldn't really be a dead end. Here's another example. Simplify the following expression without using a calculator, and the expression is cos alpha times cos 60 minus alpha minus sine alpha times sine 60 minus alpha over cos alpha times sine 45 minus alpha plus sine alpha times cos 45 minus alpha. And you notice that the numerator is just the full form of the cos addition identity, where in this case you'd be adding together alpha and 60 minus alpha. And then the denominator is the sine addition identity, where you'd be adding together alpha and 45 minus alpha, where in both cases the alpha would cancel out, leaving just cos 60 over sine 45, which you know the values as being half over 1 over root 2, which would finally be root 2 over 2, or just 1 over root 2. And the nice thing about these simplifying expressions without the use of a calculator is you can always verify the final answer using a calculator. So in this case, since you can't really just put an unknown term such as alpha in it, you could save alpha as just some random value, even something just like 50 or something, and then just type this into your calculator and then see if you end up with 1 over root 2. And if you do, then you know your answer is correct. And just a word of advice for the exam is, I guess once you've practiced a bunch of exam papers and developed a bit of a routine around how to tackle them, you should have a bunch of these techniques in mind, which you can use to verify that you've got a correct answer. And I would suggest that don't do this verification the very first time when you're actually doing the question. Rather, do this verification check at the very end once you've answered the majority of the paper and have some extra time left. And with that, we can move on to the next section of the topic, which is double angles. So what are double angles? Double angles are simply just an extension of compound angles, where when you're adding together two angles, such as in the sine alpha plus beta case or the cos alpha plus beta case, double angles is when both angles are the same angle. So it would be sine alpha plus alpha and cos alpha plus alpha. So let's see the implication of this, starting with sine alpha plus beta. As mentioned, you just make them both the same angle, so turn the beta into alpha, meaning sine alpha plus alpha, which gives sine alpha cos alpha plus sine alpha cos alpha. Notice that these two terms are exactly the same, and this can simplify to sine 2 alpha, and therefore sine 2 alpha is equal to 2 sine alpha cos alpha, and that's all it is. Then for cos alpha plus beta, which would expand to cos alpha cos beta minus sine alpha sine beta, you just change beta to alpha, making it cos alpha plus alpha equals to cos alpha cos alpha minus sine alpha sine alpha, where since the two terms consist of two of the same terms multiplying each other, this ends up as cos 2 alpha is equal to cos squared alpha minus sine squared alpha. And that's the basic form of cos 2 alpha, but by using the square identity, you can make slight variations to this basic formula. And as a reminder, the square identity was sine squared alpha plus cos squared alpha equals to 1. Then you can rearrange the square identity in two ways. One is by making cos squared alpha the subject, giving cos squared alpha equals to 1 minus sine squared alpha. Then by substituting this for cos squared alpha in this formula, you get cos 2 alpha equals to 1 minus sine squared alpha minus sine squared alpha, which simplifies down to 1 minus 2 sine squared alpha. So that's the second form of the double angle identity for cos. Then another possibility is if you rearrange this equation to make sine squared alpha the subject, which would just give sine squared alpha equals to 1 minus cos squared alpha. And you just sub this into this equation to give cos squared alpha minus 1 minus cos squared alpha, which finally comes down to 2 cos squared alpha minus 1. And that's the third form of the double angle identity for cos. Now here's a summary of the four identities we just derived, where sine of 2 times alpha, which just represents any sort of angle, would be equal to 2 times sine alpha times cos alpha. And then cos 2 alpha can be represented in three forms, where the basic form is cos squared alpha minus sine squared alpha. The second form is 1 minus 2 sine squared alpha. And the third form is 2 cos squared alpha minus 1. Let's look at an example. The question says, if cos 2a is equal to 3 over 5 and a is an acute angle, determine the following in its simplest form without using a calculator. So notice that for many of the questions in this topic, they like you to determine the answer without using a calculator. So it's worth getting some practice in this, and you should be able to do it for your exam. So for the first part, we need to determine cos A in its simplest form. And the first piece of information we can use to do this is the fact that we have cos 2a is equal to 3 over 5. So we have cos 2a, and then we can represent it using one of the three forms. And in this case, it makes sense to represent it using the form which is cos in it. So you can make cos A as the subject. So that form would be 2 cos squared A minus 1, which would just be equal to 3 over 5. Then just have to rearrange to make cos A the subject. You end up with cos squared A is equal to 0,8. And therefore cos A would just be the square root of 0,8. And in these sort of questions, they seem to really like having answers in the form of fractions with square roots and don't really seem to like having these decimal commas in them. So you could rewrite 0,8 as 4 over 5, and taking the square root of it would give you square root of 4 over square root of 5. Finally giving the answer as 2 over square root of 5. Then for the next part, we need to find the value of sine A, and you'd use a similar approach to the first part, where now you'd represent cos 2a using the form just consisting of sine A in it, which was cos 2a equals to 1 minus 2 sine squared A, which would equal to 3 over 5. And again, just make sine A the subject and solve for it. Finally giving the value of sine A as 1 over root 5. Then for part C, we need to expand and simplify cos A plus 45. So this is going back to compound angles, and would use the compound angle identity for the addition of two angles, where in the case of cos, it would become cos A cos 45 minus sine A sine 45. And since they said without using a calculator, we would substitute each of these with whatever values we know. So cos 45 and sine 45 would both be 1 over root 2, and we determined cos A in the first part as 2 over root 5 and sine A as 1 over root 5 in the second part, where for both terms the denominator would be root 5 times root 2, which is just root 10, and putting it together you get 2 minus 1 over root 10, giving the final answer as just 1 over root 10. And that concludes this example. Here's another example. If cos squared theta is equal to 0,9, what is square root of 5 cos 2 theta? So the first order of business is we need to find a way to link this term with this term. And one connection is that from the double angle identities, we know that cos 2 theta is equal to 2 cos squared theta minus 1. And we know the value of cos squared theta as 0,9, so just substitute that in. Finally, giving the value of cos 2 theta as 0,8. Then the rest is pretty simple. We have the value of cos 2 theta, so we can just substitute it into this term, meaning square root of 5 times 0,8. So square root of 4, which is just a value of 2. And that concludes example 12. So there's two more examples under this section, the first of which is example 13. If z equals to sine 50, what are the following in terms of z? First we have sine 40. So we need to see how we can link this to sine 50. So first let's try get this number to 50. The most obvious way to do this is by converting it to cos using the cofunction identity, where sine 40 is the same as sine 90 minus 50, which is just equal to cos of 50. Then to get a sine 50, we can just rewrite this in terms of the square identity as square root of cos squared 50, which is just square root of 1 minus sine squared 50, which would just equal to square root of 1 minus z squared. Then for part B, we have to rewrite sine 230 in terms of z. So as earlier mentioned, under the fundamental section, when you have an angle between 180 and 360, see whether it's above or below the halfway point of 270 to decide which of the two angles to use when rewriting it. So 230 is less than 270, so it makes sense to rewrite it in terms of 180, where sine 230 would be the same as sine 180 plus 50, which is the rule for the third quadrant, where from ASTC we can tell that this would be the same as negative sine 50, therefore negative z. For part C, we need to rewrite cos 100 in terms of sine 50. So the most obvious way the number 100 can relate to the number 50 is by multiplying it by 2. So we can rewrite this as cos of 2 times 50, which from the double angle formula would be equal to 1 minus 2 sine squared 50. Therefore, 1 minus 2 z squared. Then for the final part of this question, we need to rewrite sine negative 820 in terms of sine 50. So I included this to just give you a bit of practice for dealing with situations where you have angles greater than 360. So the first move is, notice that the angle has a negative. So sine of negative would be equal to negative of sine. So negative sine 820. Then you go about breaking this down. So first step is remove 360 from it, which gives 360 plus 460. Then the second number is greater than 360, so you have to remove 360 again, which gives it as 360 plus 360 plus 100. And 100 from the previous part we know can be rewritten as 2 times 50. Finally, breaking down the 822, 360 plus 360 plus 2 times 50. And from the property of periodicity, we know that sine of 360 plus 360 plus 2 times 50 would just be the same as sine of 2 times 50. Now this time we're dealing with the double angle formula for sine, which would be sine 50 cos 50, with a negative in front of it, of course. And since we already determined sine 50 and cos 50 in the previous parts of the question as z and root 1 minus z squared, summing that in gives the final answer as minus 2z times square root 1 minus z squared. Then for the final example of this section of the topic, we need to prove that sine 2 beta plus sine beta over cos beta plus 1 plus cos 2 beta is equal to tan beta. So the idea is we need to rewrite one of these sides and rearrange till we finally get something equal to the other side. So we could choose the left side or the right side. And it seems much easier to break this down and eventually reach tan beta than to expand tan beta somehow and somehow end up at this. So we'll break down the left hand side. Then the first obvious thing to do is to expand these double angle formulas. So sine 2 beta would become 2 sine beta cos beta, and cos 2 beta, we could represent it in three different forms as previously seen, but since we already have a cos beta in this denominator, I'll represent it using the formula with only cos in it. So the 2 cos squared beta minus 1 form, giving 2 sine beta cos beta plus sine beta over cos beta plus 1 plus 2 cos squared beta minus 1. Then the immediate thing you can see is that this one and that one would cancel each other out, giving the denominator as just 2 cos squared beta plus cos beta. Then notice that in both the numerator and the denominator, there's a common term in both the terms, where in the numerator it's sine beta and in the denominator it's cos beta. So we can factorize these out respectively, giving sine beta times 2 cos beta plus 1 over cos beta times 2 cos beta plus 1. And since these are the same, we can cancel them off, finally giving the term as sine beta over cos beta, which of course is just the same as tan beta. And then we can just flex that we've answered the question by concluding it with a hence proved. And that concludes the compound and double angles section of the topic. We can next look at how to solve trigonometric equations.